Okay, so Unit 4 is all about probability. We also have a little bit of simulation in here, some randomness, but it gets very mathy at times. It's going to remind you of math class. This is the only time of stats kind of will remind you of math class with probability. So a random process generates outcomes that are determined purely by chance. So random means chance is involved. So flipping a coin, rolling a die, these are random, processes and events that will determine some outcome. The probability of any outcome of a random process is a number between 0 and 1. 1 would mean it's going to happen, 0 would mean it's not possible to happen, and a number between would give you the probability of it happening. This is a key part of this definition, though. It describes a proportion of times the outcome would occur in a very, very, very long series of trials. So we're very good at predicting the long term in probability. We're very bad at predicting the next flip of the coin. I don't know if it's going to be heads or tails. There's a 50% long-term chance of that happening, so to speak. But I don't really know what the next flip's going to be. I'm not good at picking that out. But over the long period of time, I could describe probability. The law of large numbers says that if we observe more and more trials of any random process, the proportion of time that a specific outcome occurs approaches its probability. So long term, it's going to approach the probability. So let's say you're in a casino and you're playing a game. A lot of the games are tilted in favor of the house. Let's say the odds were there's a 92% payback. It's pretty typical. So what that means is the casino takes an 8% cut on average. But that's over a long, long, long series of trials. So let's say it's a slot machine that normally pays back 92% on average. And so again, the house, the casino is taking an 8% cut on average every time you play the game. But let's say you win on your first spin. You get $1,000, right? If you keep playing, eventually you're going to hit that long-term average of losing 8% on average over hundreds and thousands, really more like thousands of plays of the slot machine there. So it's not going to happen right away. So if you are up $1,000, you should stop playing, because if you keep playing for thousands and thousands more spins, eventually the house is going to take about 8% of your money every time you spin the wheel. So you're not going to have very much money left at the end of those spinning thousands and thousands of times, because you're losing on average 8% of your money every time you play the game, right? So it kind of will catch up to you if you keep playing. According to the Book of Odds, the probability of a randomly selected U.S. adult drinks coffee on a given day is 56%. Huh. I am in the minority there. I do not drink coffee. Interpret this probability. So this is a typical question in this section here. So how do we interpret that? If you take a very large random sample, and when we say very large, we mean thousands, not hundreds, of U.S. adults, approximately 56% of them will drink coffee that day. Wow, that's not even saying drink coffee in general, but that day they'll drink, 56% will drink. Wow, it's kind of amazing. No wonder there's so many Starbucks here, because more than half of the country drinks coffee on a given day of adults. It's interesting. One trial of the random process consists of randomly selecting a U.S. adult and recording whether or not that person drinks coffee that day. That would be one trial. But if you did many hundreds and even probably more like thousands of trials, about 56% of them will drink coffee that particular day if you ask them. If a researcher randomly selects 100 adults, will exactly 56 of them drink coffee that day? That seems unlikely to me. That's a very small run. 100 is not very much for what we're talking about here, the law of large numbers. So probably not. With only 100 randomly selected adults, the number drink coffee that day is likely to not be exactly 56. I'm not even sure how close it'll be. I would be surprised if it's more than 80% or less than 30% or something like that, but I'm not sure how close it will be after 100. There could still be a lot of variation there. If it was a couple thousand, it was in the thousands, I'd feel more comfortable. It might be closer to 56%. But again, we're talking about the long-term running average there is probability. Probably what describes what happened in many, many thousands of trials, so to speak, way more than 100 of a random process. Okay, flipping a coin. So let's do this. So we're going to get a coin out. Well, our coin will be the calculator. Okay, so we're going to go on the calculator. We're going to go rand int 1, 2, and we're going to say 1 is heads and 2 is tails. So 1 is heads. So if I get a 1, we got a heads. I got a 2, which means we got a tails. Okay, so this is my first trial. So trial 1 here. Whoops, let me get a pen. So this is my first trial. And right now we got 1 tail. So my running average is 0% heads. So I'm going to put a dot right there. I'm going to do a second trial. Got another tails. So after 2 trials, I'm running an average of 0%. Whew, not good. Trying to do the number of heads. Oh, finally get a heads. Okay, so here on my third trial, I get a head. So now I have 1 out of 3 trials have been heads. So that's 1/3, which is about 0.33. So I'm going to put a point here at about 0.33-ish. So that's my long-term running average. I've done 3 trials. 1 of them has been successful in getting ahead. So 1 out of 3 is about 33%. And so I put my dot there at 33%. That's my long-term running average here. I'm going to do 10 of these. Another tails. So that's going to be 1 out of 4, which is about 25%. So that's right about here. That's my running average is about 25% overall out of those 4 trials. 1 have been heads. We got another one. So this is 5. So the 5th one, so that's 2 out of 5, which is 40%. Fortunately, I've been able to do this in my head so far. Okay, so that's running at about 40%. We're getting closer to the 50% we expect. 2 out of 6, which is 1/3. So I'm back to 33%, somewhere around here. That's where it was a little bit ago. Okay, I'm doing another one. That's another head. So that's 3 out of 7. So 3 out of 7. I need my calculator. What is 3 divided by 7? So 3 divided by 7 is 0.42. So I'm going to go to about 0.42, somewhere in this range. Okay, my 8th simulated coin flip is a head. So that's 3 out of 8, which is that's 4 out of 8. Oh, we're golden right now, right? 3 out of 7 we were before, now we're 4 out of 8. That's 50%. Oh, we should just stop right there. So 50%, I'm right on where I hope to be eventually. It doesn't always work like that. Tails now, I'm back down. So it's going to be 4 out of 9. 4 divided by 9 is 44%. So for my 9th spin, I'm at 44%, somewhere in that neighborhood, a little bit below where I'd hope to be. See if it all works out. It doesn't always work out. I got a hit. Oh my goodness. I'm incredible here. So my luck. So after 10 tosses, I'm exactly at 50%, which is where I expected to be. Does that mean every time I toss 10 tosses of the coin, I'm going to get exactly 50%? And in case you don't know, no, it doesn't mean that. There could be a lot of variation. I might have gotten, so let's see what they had on the PowerPoint here. So this one said they did 2 trials, the green and the red. The red started out a lot of heads and then kind of made it way down. But after 10, neither one of those were at 50%. Maybe the green one was actually. But they went way down, way back up, way back up. So, but over a long term, after maybe 5,000, they're very close to 50%. So the long-term running average is very close after you get into the thousands there, but not before. There's still a lot of variation, especially early on here. So you're going to expect, if you're trying to predict the next toss or the next 10 tosses, good luck with that. We're not good at that as statisticians, but if you want to predict out of 5,000, will there be pretty close to 2,500? Pretty close. Doesn't mean it's going to be exact either, but it'll be closer. The long run average will be closer to 50% than the short run averages will be. So in the first 10, anything can happen. It could be 80%. I mean, it could be some crazy numbers there. So we just happen to get lucky. We got exactly 50%, but that doesn't always happen. In the late 2000s, an airline trained 25 pilots. 15 of them were male and 10 were female to become captains. Unfortunately, only 8 captain positions were available. So they announced they would use a lottery. So they're just going to pick this by chance. It doesn't seem like a good plan, but that's what they're going to do. So they put all the names of all 25 pilots in a hat. They shook the hat. They picked out 8 of the pieces of paper, and those 8 positions were filled. A day later, managers announced the results of the lottery. Of the 8 captains chosen, 5 were female and 3 were male. That seems at least a little bit fishy, only because it was by chance. And there were 15 males. There were more males than females, but then the ones that were chosen, there were more females than males. So I could see why maybe someone might think this was unfair. Maybe they were pulling a fast one. They said we're doing a lottery, but they didn't or something. I don't know. Or maybe this is just a result by chance. So how could we find out? So some of the male pilots weren't selected. They said they suspected the lottery was not conducted fairly. I can understand that. They wondered if there were grounds to file a grievance with the pilots union. So what could we do? We could do, this is leading into tomorrow's lesson, we could do a simulation. So you could say, for a simulation, we could say something like, let's do rand int, 1 comma 15, no wait, 1 comma 25, right? I think there were 15 men and 10 women, yeah. So if we get 1 through 15, that indicates male. And if we get 16 through 25, that indicates female. So as a class, we're going to do this. I'm just going to do one of these on the screencast. I think it'd be too much to do so many of those. But let's do one full simulation. And then the rest of the class we'll do a simulation or 2 each, and then we'll put our data on the board and see how unusual this is. Let's just find out if this simulation, just what we find out. So 1 comma 25. So I'm going to select 8 people. So this is my first person. 20 is going to be a female. Okay, so somewhat likely there. Okay, my second person out of 8 is also a female. My third person is a male. I'm just doing tally marks here. My fourth person is also a male. Fifth is a male. 3 more positions, a female, male, and male. So in the simulation, I got 5 male and 3 female. That's the opposite of what they got. That certainly does not convince me that this was a fair lottery system. So if I do more trials and find out how unusual it is to get 5 females, right now I got 3 in my very first simulation trial. But you could redo this with many, many times and maybe see if 5 is just really super unusual or if it's within the realm of possibility. So you do a bunch of simulations to do that. I think typically on the AP, they'll do the simulation part for us. We might describe the simulation, but that's how we might perform a simulation where it wasn't equally likely. You're done with the lesson. That was really looking more, that last part was looking towards tomorrow, actually. So according to a recent Gallup poll, 76% of a random sample of US Gen Z members agree that they have a great future ahead of them. Very exciting. Suppose this percentage is correct for all Gen Z members in the US. The probability that the randomly selected US Gen Z member believes they have a great future ahead of them is 76%. Interpret this probability. So again, this is a very typical example. How do we interpret probability? So what's our kind of script? What do we kind of say? Again, the key thing, you're going to talk about long term. If you have a very large random sample, so we're talking thousands, not hundreds, not tens, very large random sample of US Gen Z members, approximately 76% of them believe that they have a great future ahead of them. So it's just basically saying, if you took an extremely large sample in the thousands or more, then approximately 76% of them believe that they have a great future ahead of them. Again, the key thing is you have to talk about the very large sample. You can't just say, if you took a random sample, not good enough. You have to talk about a very large sample. If a researcher selects only 100 US Gen Z members, will exactly 76 of them believe that they will have a great future? I hope you don't say that's true, because it could happen, but 100 is a very small run of this, right? We think it's going to be closer to the 76% if we do thousands of people. We ask that many folks. So I would think probably not. Probably not. With only 100 randomly selected Gen Z members, the number who believe in they have a great future is likely to differ from 76. We don't know how different it'll be, but it probably won't be exactly 76%. That's your lesson for today.